As earlier mentioned, this is just exactly the same as the more familiar Pythagoras theorem. And the point of this section is we'll prove the Pythagorean theorem using the concepts of similarity of triangles. And the Pythagorean theorem says that for a right-angled triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides. In other words, a squared plus b squared is equal to c squared. Here's how we'll prove it. So you start off with pretty much the exact same triangle, a right-angled triangle with sides A, B, and C. And the only addition is I named the vertices as well, with A, B, and C, respectively. So we need to prove that A squared, meaning BC squared, plus B squared, meaning AC squared, is equal to C squared, or AB squared in other words. And to do this, the first step is need to draw a line perpendicular to the side AB connecting to the point C, which would look like this, where that's the new line. It's perpendicular to the side AB. Then I named the point where the line touches line AB as D. And the side C represents the length of the entire side AB. And since I've now split this side into two portions, meaning AD and DB, I'll label these new sides as well, just so we have some way to refer to them. I'll use the letters D and E. So that's the basic diagram we'll use to prove the Pythagoras theorem. And then now we'll bring in the aspects of similarity. We can note that triangle ADC and triangle ACB both have an angle of 90 degrees and both have this angle of A. Therefore, we can say that triangle ADC and triangle ACB are similar. Next, we can compare triangle CDB again with triangle ACB. So in a similar manner, the triangle CDB and triangle ACB both have a right angle. This one and this one. So that's one angle in common, and then this angle of B is also common to both these triangles. Therefore, triangle CDB and ACB are also similar. So since both triangle ADC and triangle CDB are similar to triangle ACB, that implies that they're similar to each other as well. Therefore, triangle CDB, triangle ACB, and triangle ADC are all similar. And we can use this fact to write up various proportionalities. The first is relating triangle CDB with triangle ACB. Let me go back to the diagram. So one such ratio is DB over CB, meaning the longer side over the hypotenuse of triangle CDB would be equal to CB over AB, meaning the longer side over the hypotenuse of triangle ACB. Then we can cross multiply these, and that would give CB squared is equal to DB times AB. And just for sake of simplification, I'll substitute each of these sides with the letter I designated to each of them. So this would turn to A squared is equal to C times E. Then next we can compare triangle ADC and triangle ACB. So this time I'll take the ratio of side AD over AC, meaning the shorter side and the hypotenuse of triangle ADC. And I'll equate this to the shorter side over the hypotenuse of triangle ACB, meaning AD over AC is equal to AC over AB. And cross multiplying this time gives AC squared equals to AB times AD. Then substituting this with the letters representing the sides gives B squared equals to C times D. So we can say this equation is equation 1 and this equation is equation 2. Then for the final part of this proof, we would just add the two equations together. So a squared plus b squared is equal to c times e plus c times d. And we can factorize out c on the right side, giving c times e plus d. Then if we look again at the diagram, e plus d is exactly the same as c. So we can substitute the bracketed addition of these two with c, giving c times c, which is just c squared. Therefore, a squared plus b squared is equal to c squared. And we've therefore proven Pythagoras' theorem. Or if you want to write this in terms of the capital letters, this would be bc squared plus ac squared is equal to ab squared. And that's how you would prove Pythagoras' theorem using similarity of triangles. Then for the final example of Euclidean geometry, in the following diagram, the circle with center O has a chord Fi cutting the line EG at right angles at the point H. Given this information, why is triangle EFH similar to triangle EGF? So we can demonstrate this by showing that they have two angles in common. So the first obvious choice is, of course, the right angle. And for triangle EGF, meaning this bigger triangle, that would be at this corner, since it's the angle subtended across the diameter. Then for triangle EFH, this would be the right angle, as we were told in the question. Then the other obvious option is the angle at the corner E, since this angle is common to both the triangles. And therefore, since two angles are equal, that proves that EFH and EGF are similar. Then for part B, if EF is equal to square root of 10 meters and HO is equal to 4 meters, what is the circle's radius? Let's see the diagram. So it said that side EF is root 10 meters and side HO is 4 meters. And based on this, we need to determine the length of the radius. So there's two sides over here which would represent the radius. One is the side OE or EO, and the other is the side OG. But how I'll go about answering it is by just representing the radius as an arbitrary variable x. And you'll see where I use that a few steps from now. But the first step is use this similarity to equate some ratios. So one possible ratio is EH over EF is equal to EF over EG. So for both triangles, I used the ratio of the smaller side over the hypotenuse. Then cross multiply, giving EH times EG is equal to EF squared. And this is where I'll bring in the usage of x to represent the radius. So we can rewrite EH and EG in terms of x. Let's go back to the diagram. So they told us that side HO is 4 meters. Therefore, side EH would be radius of x minus 4. And side EG would be 2 times the radius, meaning 2x. And they told us EF is root 10. So EF squared would just give a value of 10. Then expand this, and you get 2x squared minus 8x is equal to 10. Take the 10 to the other side, giving 2x squared minus 8x minus 10 is equal to 0. And all of these are multiples of 2. So you can divide everything by 2, giving x squared minus 4x minus 5 is equal to 0. Then if you factorize this quadratic equation, it comes to x minus 5 times x plus 1 is equal to 0. And solving for x, we get x as 5 or negative 1. And it can't be negative 1 because x is referring to a distance, specifically the radius. Therefore, x is equal to 5, or in other words, the radius is equal to 5 meters. And that concludes all the material to be covered for Euclidean geometry. I'll conclude this video by summarizing everything we've looked at. Here's the full summary. First, I did some important revision of all the basic concepts and theorems you need to be familiar with, as well as rules related to circles and triangles. Regarding triangles, the main concepts were similar and congruent triangles and the midpoint theorem. Then the rules for circles were the following. First is that the angle subtended by an arc at the circumference is half of the angle subtended at the center. The second rule is that equal arcs subtend equal angles at the circumference. And the third rule for circles was that if O is the center of a circle and MN is a line perpendicular to OA, then MA is equal to AN, where A would be the midpoint of the line MN. Then I looked at rules related to tangents. The first of which is that the tangent is always perpendicular to the radius at the point of contact between the radius and the circle circumference. The second was that two tangents drawn from a single point outside of a circle will have the same length. And the third point was that the angle between the tangent and the chord being drawn at the point of contact, is equal to the angle subtended by the chord in the other segment. And lastly, under the revision, I looked at cyclic quadrilaterals, which involved two rules. The first one was that opposite angles are supplementary, meaning that they add up to 180 degrees. And the second was that the exterior angle will be equal to the angle opposite to the interior angle. Then we looked at some new material, the first of which was ratios and proportionality, where I gave the definition of a ratio, which is that it's a relationship between two quantities that have the same units. And since they have the same units, the actual ratio is unitless. And while ratios give a good comparison between two numbers, they don't actually give any information about the actual values without being given any further information about the values. Then I explained proportionality, which basically just refers to the equality of different ratios. Then I looked at triangle proportionality, more specifically diagrams of triangles drawn between parallel lines, and the main point was that such triangles would have the same perpendicular height. And the first thing was that triangles with the same height will have areas proportional to their bases. And then triangles with the same height and the same base will have equal areas. Then I covered the proportion theorem, which says that a line parallel to one side of a triangle divides the other two sides proportionally. And I went to the full proof of this theorem and all the deductive reasoning involved, but it's too long to summarize in the summary section. So if you want more information on that, you should go back to the ratios and proportionality section in the video. And once proportion theorem was proven, it is pointed out that the midpoint theorem is just a special case of the proportion theorem, and it states that the line joining the midpoints of two sides of a triangle is parallel to the third side and half its length. Next, we looked at various polygons, where I first described rules pertaining to triangles and rectangles as the basis to describe the rules pertaining to the rest of the quadrilaterals. But you should already be pretty familiar with triangles and rectangles, so I didn't include them in this summary section as well. So the first new polygon I looked at was a parallelogram, and the main characteristics of it are that it has two pairs of opposite sides of equal length. So that would be this side and this side, as well as this side and this side. And then it also consists of two pairs of opposite angles, which have been indicated using the letters alpha and beta in the diagram. And to determine the area of a parallelogram, you would just say half times base times perpendicular height. Next is a rhombus. And a rhombus is characterized as having two pairs of parallel opposite sides, which is similar to a parallelogram, but the special thing about a rhombus is that all four sides will have the same length. And then, exactly like the parallelogram, a rhombus consists of two pairs of equal opposite angles, again labeled using alpha and beta. And the other special characteristic of a rhombus is that the two diagonals bisect each other at 90-degree angles, essentially splitting the rhombus into four right-angled triangles. And you determine the area of the rhombus by saying half times the product of the two diagonal lengths. Next is the trapezium. And the trapezium is characterized a lot more simply than the previous quadrilaterals, and it's just described as a quadrilateral with one pair of parallel opposite sides, indicated using the sides A and B in this diagram. And you'd calculate its area by saying half times the sum of these two parallel sides times perpendicular height h. And the last polygon we looked at was a kite, which is characterized as being made up of two pairs of equal adjacent sides, meaning two pairs of sides of equal length right next to each other. So that would be hi and ij and hk and kj in this diagram. Then they also have one pair of equal opposite angles, these lying between the sides of unequal length. So this angle and this angle. And also the diagonals bisect at 90 degrees, splitting up the kite into 4 right angle triangles. And the area is determined by saying half times product of the lengths of the two diagonals. Next, we looked at similarity, where normally two polygons are described as being similar if and only if both of the following conditions are true. These being all pair of corresponding interior angles are equal and all corresponding sides are in the same proportion. But something special in the case of triangles is that to prove that two triangles are similar, we only need to show that one of these two conditions are true. So either we need to show that the triangles are equiangular, meaning they have the same corresponding interior angles, or that they have corresponding sides in proportion. And then an extra point related to showing that a triangle is equiangular is we can prove this by just showing that two of the angles are equal. And lastly, we looked at the Pythagorean theorem, which states that for a right angle triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides. And I covered a method to prove the Pythagorean theorem using the similarity of triangles. And if you want to see the full proof, you can refer to the Pythagorean theorem section of the video. And that was everything we covered on Euclidean geometry.